So, now we will go a little bit about the reduction mechanism, though we did not talk this reduction mechanism when we were discussing about the reduction in the stake region in the blast furnace, but in this direct reduction we would be discussing about this now, and this would be again relevant to the blast furnace stake region also. So, mostly the raw material in direct reduction is in the form of pellets or briquettes, which are dense in nature. So, in direct reduction you use the ore either in the form of pellets or briquettes. So, these are actually sometimes composite, not composite pellets, but just iron or raw material iron or pellets in briquette form or pellets form. You use that one, and many times they are dense in nature. So, reduction usually occurs by removing the oxygen from the oxide of the iron in steps. So, this reduction may involve two types of broad mechanism. One is topochemical and another is non-topochemical. So, I am not going too much into the detail of this because this involve more transport processes, especially the mass transfer of the species, and which I am not sure how many of you who are taking this course, and I believe they are undergraduate students, are familiar with the transport phenomena and those mass transfer and heat transfer. That is why I consciously avoid even the heat transfer, mentioning heat transfer in this whole course, because again I am not sure how many of you are aware of it. So, the mechanism are mostly topochemical and non-topochemical. So, in topochemical reduction mechanism, the reducible gas reacts at the gas solid interface to produce iron, and further reaction takes place by diffusion of the reducible gas through the product layer to reach the unreacted material. You will understand this more in the next slide, where the figure is there. And so, but remember in this, the reducible gas react at the gas solid interface to produce iron, and further reaction takes place only by diffusion of this reducible gas through the product layer to reach the unreacted material. However, in non-topochemical mechanism, the porosity of the raw material is very high. When the porosity is very high, the reducing gas can reach almost everywhere in the pellets or briquettes. So, the reaction occurs almost everywhere in a uniform way inside the pellets. So, diffusion is not there in that case, and I know you must be familiar about this diffusion and other things, and so that terminology should not be a new one for you. So, in direct reduction of iron, the topochemical mechanism of reduction is prevalent, which is shown schematically in the figure below. So, usually this is the pellet, it is a solid line. So, it is showing the half cross section of that is of a spherical pellet. So, dense pellet of iron oxide. So, it is like a Fe2O3 pellets, and when the reducing gas is coming into the contact, either CO or hydrogen, then at the so when a reducing gas is coming into contact, it's naturally it makes near the solid a very thin film of the gas. So, that is actually what we call the gas boundary layer. So, when reducing gases are flowing through this, on the surface of the particle. So, they form and the gas actually stick to the surface of that, and that sometime in very low velocity just near the surface of the particle exist of the gas, and usually you call that one as a boundary layer. And then at this because gas is having a CO or a hydrogen, it immediately reacts with the Fe2O3 to Fe, then convert to Fe3O to FeO to Fe. So, after reduction of this, it form iron, or first it will form magnetite, then some CO will come out. So, when it will form magnetite, so oxygen CO will come out, it will become bit more porous. So, now CO2 will come out, sorry, it is after CO, CO2 will come out. So, CO will go in, CO2 will come out, that then more CO would replace the CO2 which is coming out. This CO2 now has to diffuse out through this thin layer of the gas which formed here. So, CO2 is diffused out from that, and CO also has to diffuse in through this thin layer of the gas to reach further or to reduce this further. So, then it reduces to FeO, again CO2 is formed which comes out, and this CO again diffused from that, further more CO from the outer gas through this gas boundary layer to this, and it reduce FeO and make the form the iron. Now, iron on the surface, so hematite has reduced into the iron on the surface. Now, CO can has already reduced iron, there is no more oxygen left with which it can remove. So, but still there is lots of part which is unreacted. So, what happened due to this removal of oxygen, this iron becomes porous, whatever iron is formed. So, CO or hydrogen has to diffuse now through this iron layer which is porous in nature to reach the lower oxides of iron, and it reduced them further, and the product gas also had to come out through this porous iron thing layer, and then has to diffuse also through this gas boundary layer. So, this process continues till the all pellet has reduced into iron. So, this sort of reaction where the diffusion and then chemical reaction at the interface, so diffusion of the reactant gas, diffusion out of the product gases, interface reaction, formation of this boundary layers. So, this sort of reaction which occurs is known as topochemical reduction mechanism. It is not just only associated with iron oxide, even with other sort of reaction which are similar to that, it can be associated. So, this is a typical topochemical reaction, and there are many steps which are involved into this, and some important steps actually I have mentioned here. So, from the figure it is obvious that there are many steps involved in the reduction of hematite. The main steps are diffusion of reactant gas CO or hydrogen through the gas boundary layer to reach the unreacted core. As I said, diffusion of this to reach the unreacted core, diffusion of the gas from the porous layer of iron. So, that is the porous layer of iron, reaction at the interface of iron oxide. So, then it react at the interface, diffusion of the product gas CO2 or H2O from the porous iron layer and gas boundary layer. So, diffusion of those gases. So, these are the major one, there are few other which can occur at mass transfer and other things. So, I am giving a very simple view of this non-topochemical mechanism, and very simple case we are going to consider in order to get some reaction rate or rate of change or in the weight of the pellets. So, any of the above mentioned steps can control the reduction process. So, when we say any of these steps can control the reduction process, the meaning of it, if CO is not reaching properly, or proper amount of CO is not reaching due to the very low diffusion, then this process diffusion of gases from the layer, let us say from the gas is difficult for CO to reduce, then this is sort of a your controlling mechanism, because when you are not able to get more CO due to this limitation, though other reaction may be faster and can react and can form, but this could be like a limiting step. Similarly, if diffusion of CO is quite easily can diffuse through the boundary layer, then porous layer of iron, suppose it is quite difficult gases to diffuse through that, then this may become a rate controlling step. So, the most resistance offering step usually is known as the rate controlling steps. So, any of the above mentioned steps can control the reduction process, that is the meaning of it. Without going much into the details of it, a simple model has been presented here. Assuming a dense spherical particle surrounded by the reducing gases in an isothermal condition. So, assuming a isothermal condition and the particle is surrounded by the reducing gases. So, considering that, and reaction rate is like a phase boundary control. If we consider that, then it can be expressed the weight loss with the time. So, that is why it is a negative, is equal to K(A)C). So, dW over dt is the change in weight or mass of the pellet with time. K is a constant, A is the decreasing surface area, and C is the concentration of the gas. When we said decreasing surface area, that remind me, this topochemical reduction mechanism is also known as shrinking core model. Though we are not assuming in that one this pellet is shrinking, what we are still assuming, pellet is having the same size what it has before. It might have become porous, but the size is not has not changed, but in shrinking core model usually that is shrinking. So, this boundary also the interface shrinks, and that is why we said the shrinking core model. So, C is the concentration of the gas. So, for a given time t, it may be written as, so W you know it is a weight of the particle of pellet, and we are considering a spherical pellet. So, this can be written as volume of the particle multiplied by the density is going to give you the weight. So, this is the weight of the particle at a particular time, at that instant. So, R is a variable equal to K, which is coming from here. A is the area what we are talking. So, 4 pi r square for a spherical particle, and C is the concentration, that is over here. Now, these are usually constant, the gas concentration in this. So, what we will do? We will combine this one into another constant K. So, and this when you differentiate it with respect to R. So, 3 will constant, 3 pi r square will come, and 4 pi will get constant through this. So, you will get minus dr over dt equal to k by rho. So, now this so rho is the density of the unreacted sphere. Now, this is a very simple equation which you can integrate it, and knowing that at time t equal to 0, that before starting the reaction, your radius of the pellet is the initial radius. So, at t equal to t naught, that is at the initial time, radius of the pellet is equal to the initial radius of the pellet. So, if you integrate it between these limit, then essentially, so dr 0 to r naught, and this is a constant dt 0 to t. So, you will get r naught minus r equal to k t by rho. So, this is the equation which can be simplified further. So, if initial weight of the pellet is W naught, then the fraction reacted alpha can be given as. So, now here we are introducing a definition of fraction reacted, how much fraction has been reacted of the pellet by the gas. So, fraction it can be given by then. So, initial weight of the pellet minus the weight of the pellet at that time at an intermediate time divided by W naught initial weight of the pellet is going to give you the fraction reacted. That the way you define the fraction reacted, which is nothing 1 minus W over W naught, which is nothing 1 minus W, as we said, the weight of the particle at that instant. So, it is 4 by 3 pi r cube rho divided by initial weight of the particle. So, this is 4 by 3 pi r naught cube, that is the initial radius of the pellet divided by rho. So, essentially this would be get cancelled out, or this r by r naught q equal to, and you bring that one here and this goes there. So, that becomes this, if you bring this one here, this is there 1 minus alpha, and r by r naught equal to 1 minus alpha to the power 1 by 3. And this we did it because we are having our relation here like this. So, this also will be divided by r naught, because that is known. So, we combine this equation with this equation, then we can get 1 minus alpha to the power 1 by 3 equal to k rho r naught t. So, this gives us a relation about and from using this relation one can calculate the fraction reacted in a given time. So, many similar expressions can be obtained for the fraction reacted depending upon the uses of reaction controlling mechanisms which were described before. So, as we said, there are many mechanisms which can control the reaction, and depending which mechanism you use, you have to start the reaction equation this accordingly. That will change, and then you will follow with that one, and you can get a little different expressions for that. So, now and this is actually more about the topochemical reaction, and if it is a non-topochemical reaction, which where we said there is no resistance to diffusion or reaction, the reaction occurs everywhere. So, it follows the first order reaction kinetics, especially for iron oxide reduction, and in that way it is expressed in this form, which gives you this fraction reacted things, and can be converted again to that form r by r naught. So, this is for the non-topochemical reaction, the reaction kinetic is. So, I think now probably it is the time to for a numerical by which you can understand how this reaction kinetics works and how one can calculate the various parameter and other things. So, this example shows consider the reduction of a spherical Wurtzite pellet by hydrogen into the metallic iron at 700 degrees Celsius. Calculate the unreacted radius of Wurtzite after 3 minutes. The initial diameter of the Wurtzite is 1 centimeter and density is 4000 kg per meter cube. The value of constant K may be taken as 0.0882 kg second per meter square. So, these are the parameter which is given, and what is needed to calculate the radius of the unreacted Wurtzite after 3 minutes. So, what we need? We need actually first the fraction. If you look at this one, that fraction reacted is needed. So, first, so mass of this pair we know 4 by 3 pi r cube rho. So, density is given, radius is given. So, if we substitute these values, we get the mass of the pellet or sphere 2.09 into 10 to the power minus 3 kg. Now, we know one from the reaction kinetics, considering it is a phase boundary control, 1 minus alpha is equal to K T rho r naught. So, here now everything is known, K is given, time is given 3 minutes, rho is given, r naught is given. So, if we substitute that value, K T unit converted into second, 3 into 60, 180 second divided by density and the radius of the particle, that gives you 1.7938, and which of course will give you, when you bring this one to this side, so subtract from 1, it will give you 0.2062, and finally 1 minus alpha will give you 0.59 and alpha will give you 0.41. So, the fraction reacted would be 0.41 really. So, alpha, now you know fraction reacted can be represented by this W naught minus W, that is the radius at that time. So, here in this case the radius of the pellet after 3 minutes, W naught is the initial one weight. So, from this we can calculate. So, we know the initial weight or mass of the particle is given this minus 4 by 3 pi r q r I 3. So, r I is the instantaneous radius, the radius at that time, which here is 3 minutes after that, rho divided by W naught, initial weight of the pellet, and so that gives you 1 minus, then after some manipulation of this 1 minus 8.01 into 10 to the power 6 r I cube. Now, fraction reacted we know, we already calculated 0.41. Now, everything is known. So, r I cube would be this one and r I would be this one, which means about 4.25 millimeter. So, 4.25 millimeter radius would be there of the unreacted Wurtzite after 3 minutes. So, which means almost 1.5 millimeter diameter has been reacted and formed iron. So, this gives you an idea how one can calculate the various parameter or can obtain the unreacted radius of the pellets and thing.